So we're back, and we're now going to be talking about the second of the conservation laws that we promised we would cover, that of momentum conservation. And as I said, momentum conservation is essentially just Newton's second law of motion, F equals ma, except with some notable differences when it comes to fluid elements. We are not talking about F equals ma for point particles or for rigid bodies. We're talking about F equals ma for a fluid element, right? So the right hand side here, ma, is simply the rate of change of momentum. The left hand side, well, is simply the force acting on the fluid element, right? So there are two reasons the momentum can change. It can be so what we've written down here is, when we say momentum, in this case we are really talking about rho u. This is what we really momentum per unit volume. Okay, so rho u is momentum per unit volume, right? So this momentum per unit volume, when you integrate over a volume element, it becomes simply momentum. So the momentum can change because there's an intrinsic, there's a d over dt kind of, there's an actual change of momentum within the volume. It can also change because there's a flux of momentum through the bounding surface, right? You know, in order to get the mass flux, mass flux was just, you recall, for instance, right? And momentum flux, well, momentum times u, in a way. Not quite. What's the main difference here? This is a scalar, whereas this is a vector. So therefore, the momentum flux, while mass flux is a vector, mass flux is a vector, but because momentum itself is a vector, momentum flux is essentially rho u u, where it's not a u dot u, it's an outer product, not an inner product, and so this is a tensor. We will discuss this. We will sort of specify what exactly rho u u is, and we'll come to it. But just wanted to draw the analogy. In order to get the mass flux, you simply multiply the mass density with the velocity. In order to get the momentum flux, you simply multiply the momentum density with u, momentum density, sorry. And that gives you the momentum flux. So the momentum can change because of intrinsic change of momentum inside the volume, and also momentum flux through the bounding surface, just like we discussed for the mass continuity equation. There's a bounding surface and there's a flux of momentum through the bounding surface, either outside or inside, and then what you do is you do an integration over the surface element, right? And you add both of this up before doing that, just like the surface integral, I beg your pardon, here I'm calling a surface integral element dA, and here I'm calling it ds. It's really the same thing. Okay, so you can just like we use Gauss's divergence theorem for we use Gauss's divergence theorem in this situation. Yeah, just like we use Gauss's divergence theorem in this situation to go from here to here. Okay, Similarly, we are going to use Gauss's divergence theorem here in order to convert the surface integral into a volume integral, except the divergence theorem that we will be using is for tensors, and simply because the momentum flux is now a tensor. So we can use this, we can transform the surface integral into a volume integral like this. Okay, and so go from here to here using Gauss's divergence theorem. So the rate of change of momentum is this. Now notice how similar it looks to what we wrote down for the continuity equation, for the mass conservation equation, except instead of just rho, you have rho u, right? And the flux is essentially rho u where this is not an inner product, it is an outer product. So this quantity is a tensor. Okay. The reason we went from the surface integral to the volume integral was because this term was in terms of a volume integral, and you want to put both on the same footing, and so that's what we do. And as before, this statement is valid for arbitrarily small volumes. Okay, and so if the dV is taken to be arbitrarily small, the integration essentially becomes invalid. I mean, since we are integrating only over one volume element, and that means that the integrand itself is equal to 0. Just like notice the analogy with what we did for mass conservation is exactly the same. So before saying that, we said F equals ma. So far we have only done ma here. Yeah, and what is F? The rate of change of momentum is equal to force, of course. This is F equals ma. This is Newton's law, and the force on the fluid element can have a volume component due to body forces, say due to gravity. Yeah, and that can be written as rho g dV. Yeah, now g is really a proxy for any kind of body force. It can be gravity, it can be some other kind of body force also. By body force I mean a force that's acting all throughout the fluid, not only on the surfaces. Okay, it's acting throughout the fluid, throughout the body of the fluid, like gravity. So in that case you would have to integrate all through the volume and not merely on the surface. Surface forces are a little trickier. So forces can be acting throughout the body of the fluid, for instance gravity, but they can also be acting on a surface. One example of a surface force, pressure. Yeah, pressure is force per unit area, of course, but the pressure acts only on the surface. And as we have discussed earlier in the course, pressure is only one element of the stress tensor. That's the normal element. Yeah. And the other components of the stress tensor are shear stresses, which are essentially on the same footing as that of pressure, force per unit area, except the very fact that you are talking about area means you are talking about the boundary. So this is what we just said. Recall, we can have forces that are on a surface area element that are normal to it as well as tangential to it. Like here, you see you have a normal force as well as a tangential force. These are tangential forces. These are forces that are, the normal force acts in the same direction as the vector that characterizes the surface element, right? So this is the outwardly directed normal that characterizes the surface element, and the normal force is acting along the same direction, whereas the tangential forces are along the surface. This can be an example of a tangential force. Another example of a tangential force can be one which is acting into the plane of this screen. Yeah. So taken together, forces these kinds of forces are called shear forces. And so these are the two different kinds of forces. The main difference between a body force and a surface force, well, is surface force acts only on the surface. Whereas body forces act throughout the body of the fluid, not only on the surface, right? So The ijth component of the pressure tensor represents the force in the ith direction felt by an area element whose outward normal points in the jth direction. Let's pause for a minute and try to understand what this means. Let's draw a little box like this, and so let's say x, y, and x cross y would be, I believe this would be z. Yeah. So you can have a force that's acting like this. You can also have a force that's acting like this, right? So force in the ith direction, suppose this is the I direction, and the area element is characterized also by the I direction, in which case the force would be P I I. And anything else, any other force like this would be something like a P I J. Okay? And the J would be something like this. So if that's the ith direction and this is the jth direction, yeah. So the J in this case would be along the y axis, and the I would be along the x axis, right? So something like this would be Pxx, whereas something like this would be a Pxy or Pyx, right? So that's all this is. This is simply accounting for the fact that you can have there is something called a pressure, which is ultimately at the end of the day it's a dF over dA, except the direction of the F and the direction of the A need not be the same. One can be along I and one can be along J, and I need not be the same as J, in which case you need to have something in between. This is just a matrix multiplication, right? So this is a vector and that's a vector, so by necessity what's in between needs to be a matrix, and the elements of that matrix are the elements of the pressure tensor. The diagonal elements are simply the scalar pressure. The off diagonal elements like this are the shear stresses. Okay? So when you integrate this, the F surface, the ith direction of the F surface is, when you integrate over the surface element that points, whose outward normal is along the jth direction. Okay, so you integrate that, and you apply in order to go from here to here. Again, you apply Gauss's divergence theorem. It's the same thing. You went from an area integral to a volume integral, and this thing is nothing but a divergence. Okay, just written in a different kind of form. This is just a divergence. So it's the same thing. You went from an area integral to volume integral, and in doing so you would encounter a divergence, and this is just that. So this is just an application of the Gauss's divergence theorem, right? So the total force on a fluid element would be a body force and surface forces. And by using Gauss's divergence theorem, you convert the surface integral into a volume integral like that. The advantage being you can put both of those on the same footing, and you can have a volume integral for the whole thing, exactly like we did for the mass conservation equation. No difference. Okay, so this is the total force. So this is the F, and we did the MA here. So we equate this to F. Yeah. So this is the finally the when I write divergence of P, the P is really a tensor. So the divergence of a tensor is defined by this. The ith element of the divergence is simply dpij dxj. That is how divergence of a tensor is defined. You really don't need to know much more about tensors. This is good enough. We will move to slightly less complicated. I mean, this is the most general way of writing down the momentum conservation equation, and don't despair if this seems a little too involved for you. I just wanted to write down the most general way and then reduce it to slightly more familiar forms, such as the Euler equation. We will get to that in a minute. So, taken together, so this was F, and we've already written down Ma. Taken together, the momentum conservation equation is this. So, this would be the F and this would be the okay. And here is what I just said. I said a few slides ago that the quantity UU, this is an outer product. Okay, it's a second order tensor in the sense that this is how the outer product of two vectors A B is defined. Yeah, and this is the matrix A1 B1, A1 B2, so on and so forth. So that's what UU is. If you're wondering what an outer product is, well, this is an outer product. Okay. Now, does this look familiar? If you did not have this pesky UU here, and if you only had the rho here and the rho u here, this would be, and of course the right hand side would be 0, this would just be the mass continuity equation. This is the momentum continuity equation, right. So now, if only for some reason the right hand side was 0, if this was 0, then writing the left hand side equal to 0 would be the conservative form of the momentum equation. In other words, if there was no pressure gradient, there were no body forces, then either that, or if there are no body forces and you are able to somehow cleverly take this pressure gradient into this term, absorb all the elements of the pressure gradient of the divergence of the pressure tensor into here, then we can write down the momentum conservation equation in a conservative form, and that's what we will try to do here. You neglect body forces. That's one thing first, and doing exactly what I just said, you take this in here, which is again of the form partial time derivative of the quantity plus the divergence of the flux of that quantity is equal to 0, right. So, this is the conservative form of the momentum conservation equation. Now, let's simplify things a little bit. For an inviscid fluid, it's enough to consider the scalar pressure. In other words, it's enough to consider the diagonal terms of the pressure tensor, just the diagonal terms, where the delta Ij is equal to 1. Well, by definition, the delta Ij is equal to 1 only when I is equal to j. Okay, in other words, only for the diagonal elements. When I is not equal to j, it's equal to 0. So, turns out for an inviscid fluid, it's enough to consider just the scalar pressure. Now, maybe it's worth pausing a little bit to figure out why this is so. You see, the whole concept of viscosity arises when you have a situation such as this, where you have, these would be the velocity vectors, yeah, of a viscous fluid which is flowing along the x direction, and that's why. So, only when dux dy is not equal to 0, you need to think about viscosity, yeah. And this happens only when there are shear forces. In other words, here you see there is a shear. This is the definition of a shear, okay. In other words, also you can also say that there is rotationality in the fluid, okay. Unless there's shear, there's no point thinking about the viscosity is irrelevant, okay. And when there's shear essentially represents, so the diagonal elements would be this would be Pxx, Pyy, Pzz, and the off diagonal elements, which are the other ones, okay, these represent shear. No shear, no point in in thinking about viscosity, because this shear is you can think about this shear as due to little rubber bands connecting the two layers together and refusing to let the layers slide freely. Yeah? No shear, no viscosity. Okay? In other words, no off diagonal elements, no viscosity, or no viscosity, no off diagonal elements. In other words, when you are talking about an inviscid fluid, which is a fluid, in other words, inviscid meaning no viscosity, that is what it means. Okay? For an inviscid fluid, there is no need to worry about the off diagonal elements. It's enough only to consider the diagonal elements. In other words, you can write the P tensor as some scalar times delta I j. So, which is non-zero only when I is equal to j. Okay, so that is what I mean here. And yeah, in other words, only the diagonal elements of the pressure tensor are non-zero. You realize we are simplifying things from what we saw in the last slide, where we retained everything in Pij. Okay. Furthermore, we expand this. This is still the most general equation. We expand this and use the mass continuity equation. You use the mass continuity equation, which was this is the mass continuity equation, right? So, you use this in here. Yeah, so this is the mass continuity equation. You use this in here, okay, you expand this out and you use this in here to get what is called the Euler equation. Okay. So, there are three things that you need to consider. Number one, the pressure tensor is greatly simplified in that only the diagonal elements are important, right, and really that is the main thing. And the second thing is you do need to use the mass continuity equation, okay, and then the momentum equation becomes this, and this is called the Euler equation, and the Euler equation is valid only for inviscid fluids. In other words, situations where the viscosity is not important. And it becomes like this, and there is a simpler form of the Euler equation which you will find in Arnab Rai Chaudhury's book. It follows the Lagrangian treatment. In other words, you write down an F equals ma sitting on top of a fluid parcel. And right, keep in mind that the Euler equation is valid only for inviscid fluids, in other words, fluids where the viscosity is negligible and you can really set the viscous terms equal to 0. Equivalently, the off diagonal elements of the pressure tensor are 0, and only the diagonal terms are non-zero. Else there are additional terms in the pressure tensor which involve viscosity, and you get the Navier-Stokes equation. So, the Navier-Stokes equation is a momentum equation when you include viscosity, and the Euler equation, which is this one, is valid for situations where viscosity is not important. In other words, it is valid only for inviscid fluids. So, we will stop here and we will consider a few other aspects before we move on to the full Navier-Stokes equation.